Imagine asking, what if I'd taken a different treatment? Would I have recovered? That's a counterfactual, a hypothetical rooted in causal reasoning. In classical science, even with perfect data from observations and interventions, some counterfactuals remain unidentifiable. Why? Because different underlying causal models can produce the same observed outcomes, but disagree on what would have happened under a different choice. Now here's the twist: quantum oracles change everything. In a simple binary case, where a hidden variable determines how one variable affects another, classical data gives you only two constraints. But with a quantum oracle, you can coherently probe the system using superposition states, like plus and measure in the Bell basis. This gives you a third independent constraint, one that classical probing can never access. The result? You can fully reconstruct the distribution over causal functions, and thus identify all counterfactuals, including ones previously impossible to pin down. This isn't just about speed. It's about identifiability. Quantum oracles allow you to uniquely determine two-way joint counterfactuals, like, what's the probability y would be 0 if x were 1, given we saw x equals 0, y equals 0, which classical oracles can't. And while you can't fully identify three-way or higher joint counterfactuals, even quantum oracles give tighter bounds than classical ones, a clear advantage in partial identification. But is this truly quantum? Surprisingly, no. In the binary case, even a classical-like theory, Spekkens' toy model, can replicate this advantage. So the edge may not come from contextuality, but from coherence. This work redefines oracle problems, not just testing if a function is constant or balanced, but learning the full causal structure behind it. So yes, in certain settings, quantum resources give a causal advantage. Not just for computation, but for understanding what really causes what. And that's the power of quantum causal inference,